All right, mathematicians, here we've got a quick test review for our Chapter 4 test in math analysis. Just like we saw in class, we're going to have some graphing. First graph the parent graph, then do the transformations. This is an exponential function. An exponential function has a domain of all real numbers, but the range will be limited to powers of 3, which are all strictly greater than 0. So 0 to infinity is our range. Remember, for these, we will have a horizontal asymptote. And that horizontal asymptote for the parent function is going to be at y equals 0. So if you want to make yourself a little xy chart, go for it. -2, -1, 0, 1, 2. So 3 to the -2 is 1/9. 3 to the -1 is 1/3. 3 to the 0 is 1, 3, 9. And then you can quickly graph those points. And there is our parent function. Now, to draw our transformation, we've got the quantity including x is x plus 2. So if x plus 2 is set equal to 0, we see x equals -2. So this function is moving to the left 2, and it is also moving down 4, which is going to give us a new horizontal asymptote at -4. So the graph is simply moving down 4 and 2 to the left. And you can just translate all of those points. So 1, 2, 3, 4, and then 2 to the left. 1, 2. So there's a point. 1, 2, 3, 4, 1, 2. 1, 2, 3, 4, 1, 2. 1, 2, 3, 4, 2. And then 1, 2, 3, 4, 1, 2. So here we go. Here is our very basic translation of an exponential graph. Next, the logarithmic graph. So the logarithm is the inverse operation of the exponential function. So the logarithmic function has a limited domain. Take whatever the argument is and set it strictly greater than 0. So our domain is going to be all positive numbers, but the range will be what we saw for the domain of the previous one. The range will be all real numbers. So the exponential functions had a horizontal asymptote. The logarithmic functions will have a vertical asymptote. So a vertical asymptote right here at x equals 0 for the parent function. And once again, if you feel good about making yourself a little XY chart, do it. Just do it quickly. Remember, we pretty much only want to plug in powers of 2 here. Those are going to be the easiest things to graph. So 1/4, 2 to what power is 1/4? -2. 1/2. 2 to what power is 1/2? -1. Plug in the 1, 0. And then 2, 1. And then 4, 2. So plot those points over 1/4, down to 1/2, 1, 0, and you see how these points are just the mirror image of basically the graph that we were just plotting. So there's our parent graph. Now, to the other side, take this quantity, whatever it is that's inside of the parentheses, that is the argument of the logarithm, set it greater than, strictly greater than 0. X must be greater than 3, so our domain is 3 and everything bigger. The range is still all real numbers here. So our graph is going to be moving 3 to the right and up 5. So if we're moving 3 to the right, that means our vertical asymptote is also moving 3 to the right. So all the points are moving 3 to the right and up 5. So 1, 2, 3, 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4, 5. And then 1, 2, 3, 1, 2, 3, 4, 5. So here is our new translated function. So those are the graphs. We're going to see an exponential function and a logarithmic function. So back by popular demand is a half-life problem. Strontium-90 is a radioactive substance that is a waste product from nuclear reactors. The half-life of strontium-90 is 28 years. Find the decay rate. So we're given the time that it takes for half of a substance to decay away. We need to find the decay rate. And like we talked about in class, it doesn't matter the amount of the substance. So you can let your A sub O be whatever you want, or you can just leave it in terms of A sub O, which is what I'm going to do here. So if I want to know the decay rate, I'm looking for K. And since it is a decay rate, that K value must be less than 0. We are anticipating that it will be negative. So our formula for growth and decay is A equals A sub O times E to the KT power. So let's start plugging in what we know. First of all, remember, this is half-life. Half-life is indicating that half of the substance will remain after 28 years. So if A sub O is the initial amount and I only need half of it, then I'm going to replace A with 1/2 times A sub O equals A sub O times E to the K, which is our unknown, times T. T is 28 years. So this is the equation. And just like we've talked about in class, every single time, it's all going to cancel away, and the only thing that's going to remain is 1/2 because we're only going to be left with half of our initial amount. So 1/2 equals E to the 28K. And like we've discussed in class, anytime that you see the natural number E, be on the lookout for an opportunity to use ln. We're going to do that here because when we introduce the natural log to both sides of the equation, it supermans that power to the front, and ln of E, of course, is 1. So we are left with ln of 1/2 equals 28K, and you can just go straight to your handy-dandy calculator and calculate that. So let's go ahead and divide by 28, and we're going to get our K value. So ln of 0.5 is that divided by 28. We have a decay rate of negative 0.02476. Don't be harsh with your rounding. Take it way out there because the more digits we have, the more precise our calculations are going to be. So now let's read this second part of the problem. If by accident 60 grams of strontium-90 is released, how long will it take for it to decay to a level of 10 grams? Now we actually are given amounts that we can plug into the equation, but we now know the decay rate, so we can rewrite the whole model. So the model for strontium-90 is that A equals A sub O times E to the negative 0.02476 T. This is the model that we'll use for strontium-90. So once again, our initial amount is going to be 60 because by accident 60 grams is released into the atmosphere. We want to know how long is it going to take to decay to a level of 10 grams. So we want 10 grams to be left after an initial amount of 60 is released. So this is what your equation should look like. And once again, how long, when the question says how long, we are solving for T. So start by doing inverse operations to isolate the T. So we're going to start by dividing both sides by 60. So we get 1/6 equals E to the negative 0.02476 T. Once again, introduce the natural logarithmic function to both sides of this equation. Superman that power to the front. So now we've got ln of 1/6 equals negative 0.02476 t. Divide by that little decimal number, and we are going to solve for t. So once again, follow order of operations carefully. So ln of 1/6 is that divided by negative 0.02476. Now before I even hit enter, anticipate that since we are solving for time, our answer better be positive. Of course it is 72.37 years. 72.37 years for 60 grams of strontium-90 to decay to 1/6 of its original amount. One last question. We will have several logarithmic equations to solve on our test tomorrow. Remember, the best thing to be on the lookout for is, do you have an opportunity to apply the properties of logs? And we have a single logarithm set equal to a sum of two logarithms. So if we have a sum of logarithms, use your product property and condense the logarithms into a single log. So log base 4 of 2x plus 1 equals log base 4 of x minus 3 times x plus 5. Remember, if the logs are positive, the arguments stay in the numerator of the logarithm, and if they are negative, they go to the denominator. Don't make it complicated. Once we have a single logarithm set equal to a single logarithm, then by the one-to-one property, we can cancel those logs and then set the arguments equal to each other. 2x plus 1 equals x minus 3 times x plus 5. Let's do some good algebra now. Combine those two binomial expressions, x squared plus 2x minus 15. Then from here, cancel the two x's, take the 1 over, 0 equals x squared minus 16, which is the DOTS, the difference of two squares. Factor it, and we get x equals 4 and negative 4. But don't stop there. Be sure to check the validity of your answers and be certain that they exist within the domain restrictions of this function. So, if 2x plus 1 must be greater than or equal to 0, then x must be greater, not equal to, excuse me, strictly greater than 0. Then x must be strictly greater than negative 1/2. If x minus 3 is greater than 0, x has to be greater than 3. And if x plus 5 is greater than 0, x has to be greater than negative 5. So, duh. Choose that highest value, which is x must be greater than 3. Our answers have to be greater than 3. Negative 4 is not. So our solution set is simply x equals 4.